Here is an applied force problem where we have two trees, or really they could be any two posts, and we have a rope tied between them. And we've got an angle theta, which is the angle between where the rope comes out and the post, and the tree trunk. And the problem is asking us to find two different types of tension within the rope. Now, I like this problem a lot because, first of all, it reminds me a lot of a hammock. And in fact, I think that's probably what inspired this problem, actually, since it's got kind of a neat application there, where if you were like an engineer and you were designing a hammock, then it'd be very important to know what forces it can withstand, whether it can withstand a proper force against the trees, and how much force it can withstand at the middle of it, if that's where a person is going to be laying down. So it's got some applications there. And another reason why I like this problem a lot is because it's a good example of a problem that you have to think about a certain way to get the hang of it. Like, this problem is not nearly as hard as it might seem at first glance. When a lot of people I know, a lot of people I've seen who've tried to solve this problem, a lot of the times they'll try some crazy complicated solution, like to use calculus or something to sum up all the forces along the length of the rope, or something complicated like that. When in reality, there is a pretty clever way to look at this problem that actually makes it a lot simpler. It's actually not that hard. And the way that you can make this problem a lot easier is to draw a free body diagram of the rope. But instead of drawing a free body diagram of the entire rope, you could just draw a free body diagram of just half the rope. And it might seem odd, but if you do it like this, then this actually simplifies things a bit. Where first off, you can draw, in our free body diagram, here the tension coming to the middle of the rope, which is part of what we're asked. And then on the other end, that's where the tension at the end is going to be, at one end of the rope is going to be. And of course, there's also a weight acting downwards on the rope. But since this is only half the rope, we'll say that this is the weight divided by 2. So that is our free body diagram for this problem. And we already know that since, ideally, the rope's not falling or breaking, the net force in all directions is going to be 0. So we can start setting up some force equations. But before we do that, I first want to get the directions. I want to get the components of the end tension squared away. Because we already know there's going to be an angle theta here. But because in geometry vertical angles are equal, this angle will be theta as well. And the reason why this is relevant is because in our force diagrams, in our force equations, we'll want to have an x and a y component for t sub end, because it goes in two different components, it goes in two different directions based on what this angle is. And if we use some trigonometry, we can see that the x component of t sub end is going to be equal to t sub end, the net one, times the sine of theta. And the reason why that is the case is because sine is the opposite side of the triangle, which is going to be this horizontal component here. And for t sub y, that's adjacent over hypotenuse. So in that case, that's cosine. So those are our components for t sub end in both the x and the y directions. Now let's write out some force equations. So the net force in the x direction, we already know right off the bat it's going to be 0, since there's no acceleration in the horizontal direction, at least none that's explained to us by the problem. It wouldn't make sense why we'd want that. And we know, and we can see that in the x direction we will have t sub mid positively in the right direction. So I should probably first note that, like our coordinate system here, so that's to the right, that's positive x, and upwards, that's positive y. So that's t sub mid positive, and then in the negative x direction, that's minus t sub end times the sine of theta. In the net y direction, again, no acceleration, so this is equal to 0. And positively, that's going to be t sub end times cosine, the y component, of the tension in the end of the rope acting on the tree, minus, and then that's going to be the weight, so that's minus W over 2, since the weight is acting downwards. So these are our force equations for the rope. And now let's actually try, now we've got two equations and two unknowns, so now let's try rewriting this to solve for the tensions. Let's first try to find the tensions at the ends of the rope. So this second equation here has only one unknown, t sub end, so let's start there. If t sub end times cosine of theta minus weight over 2 is equal to 0, then that alone will be enough for us to algebraically solve for t sub end. So if we add w over 2 to both sides, then t sub end times the cosine of theta is equal to the weight over 2. And then solving this for t sub end, we just divide both sides of this first equation by cosine of theta. So that's weight divided by 2 times the cosine of theta. And that is a formula for the tension at the end of the rope. Now let's try solving for the tension in the middle. So using the same logic that we just used, we can see from the first equation, the net force in the x direction, that T mid is going to be equal to T sub end times the sine of theta. And as we just established, T sub end is equal to the weight, W over 2 times the cosine of theta, times the sine of theta. And the sine of theta is in the numerator and cosine of theta is in the denominator. So if we want to simplify this further, we can replace that with the tangent of theta, since tangent of theta is defined to be equal to the sine of theta over the cosine of theta. So the tension at the middle of the rope is equal to the weight times the tangent of theta divided by 2. And that is our tension at the middle of the rope. So with that, we now have the tensions at both points in the rope. Thanks for watching. I hope this video helped you out, and if you have any questions, please leave a comment down below and I'll try to help you out. If you have a request for a future video, comments work there, but I've also got a Discord server linked in the description, so all are welcome there. And if you'd like to support this channel and help me make more of these in general, feel free to check out some of my other videos on this channel, as well as the ones I've got coming in the future. So that's all for now, and have a nice day.